Hi, welcome back to es346 Basic Thermodynamics. This is module 2.4, where we'll discuss the first law of thermodynamics. The corresponding sections in the textbook are 2.6 and 2.7. Okay, here are the two learning outcomes for this module. First, we will look at using the first law in equation form, and then second, we will define what the efficiency is for single and multi-step processes. So I want to start off with sort of the three energy rules. These are rules that energy transformations must abide by. So first I list that the total amount of energy is constant. You cannot create energy, you can't destroy energy. This is what's known as the conservation of energy, or the first law of thermodynamics. Now, energy can be transferred between systems, and in the last few modules we've looked at ways to do that. We've looked at energy transfer by heat, and we've looked at energy transfer by work. And the last thing is that energy can change forms. In the very first module, we looked at several of the different forms that energy can take. Okay, so based on those energy rules, let's go ahead and formally write down what the first law of energy, the first law of thermodynamics energy balance would look like. So as I said, that the change in energy, since it can't be destroyed, can only be the energy that we put in minus the energy that we take out. In this respect, it's a lot like money. If I have money in my bank account will change by how much I put in minus how much I take out. So now, what we're looking at are thermodynamic systems where we can do energy transformations by work and heat. So if I think of this box as my system, I could put energy in by heat transfer, and I could put energy in by work interaction. Likewise, energy can leave my system also by heat transfer or work interaction. Now, if those are not balanced, there's going to be a change in energy inside the system. It could go up, it may go down, or in some instances, it may remain zero. Let's go ahead and put these Q terms over to the right-hand side of this equation. So I have the change in energy is going to be equal to the heat transfer that goes in minus the heat transfer that goes out, plus the work that goes in minus the work that goes out. So this right here is sort of a formal writing of the first law of thermodynamics. Okay, let's go ahead and apply that to a couple examples here. So here's the first example where I have a pot of water and it's boiling and heat is entering the system, maybe by some sort of convective heat transfer. It's coming in at 15 kilojoules of energy goes in, and it's also losing energy. It loses 3 kilojoules of energy. So if I was to write the energy balance for this, the change in energy of my system is, well, what goes in, I have Q going in. I also have energy leaving, I have Q out. So if I put in the numbers that are shown in the diagram here, Q in is 15, Q out is 3, and that tells me that the change in energy is going to be equal to 12 kilojoules. Let's go ahead and look at another example where now what we have is a work interaction. First of all, from this diagram, there's a word here that says adiabatic. And whenever you see the word adiabatic, it has a very particular meaning in thermodynamics. It means that there's no heat transfer. So what that says is that Q going in is equal to 0, and also Q going out is equal to 0. So it's a key term when you read problems related to adiabatic systems. So let's go ahead and write our energy balance for this equation, or for this system. The change in energy is going to be equal to, well, there's no heat interactions, and what we have now is a work interaction. We have boundary work going in as the system is being compressed. So that's going to be W in, and that's given as 10 kilojoules. So we realize that the change in energy of my system is 10 kilojoules. All right, let's look at one last third example. A little bit more complicated. I've got a few more terms here. Here I have this rigid box. This system is not adiabatic. I have shaft work going on, which means that this fan in here is spinning. I've got heat transfer going in and heat transfer going out. Go ahead and write our energy balance for this system. The energy that goes in, we've got a Q in term, and we also have a work going in term. And then we have one energy transformation out, which was Q out. So putting the numbers in that are shown in the diagram, Q in is 15, the work going in is 6, and the energy leaving is 3. So I have 15 plus 6 minus 3, and that would be equal to 18 kilojoules. So that's my change in energy. All right, let's go ahead and move on and talk about thermodynamic efficiency. And I like to define thermodynamic efficiency as the ratio of what's desired over what is required. So if I have some thermodynamic system and I talk about the efficiency of it, something may go in that's required, and then what comes out would be what is desired. So for example, if I was to put 5 units of energy in, and I was only to get 4 units of energy out, well, desired over required would be 4 over 5, or 0.8. I would call that 80% efficiency. Now, we know from the energy balance we were just looking at, what this means is my system is also losing 1 energy unit out. The system on the top here. This would be an energy loss. Okay. Now, I can go ahead and combine various systems. Let's look at another example. Say I have system A right over here, and it is 75% efficient. And I'm going to go ahead and put 8 units of energy into that system. And then what comes out of there, I'm going to go ahead and put into a second system I'll call B that is 50% efficient. And then we'll see what comes out on the far side. Well, if I put 8 units of energy in and it's 75% efficient, that means I will get 6 in this intermediate stage, and 6 going into my second system means that I will get 3 out. So if I look at my overall efficiency of what I get out versus what I put in, my overall efficiency is 3 over 8, which is about 37.5%. Now, I could have calculated this another way. If you look at the two efficiencies I have, 75% and 50%, if I multiply those two by each other, so 0.75 by 0.5, I would realize that that is equal to 0.375, or 37.5%. So therefore, if I want to look at a system, or a series of several systems, the overall efficiency, I go ahead and multiply the two efficiencies together. So for example, A to A times A to B would end up being the overall efficiency. All right, let's just talk about a couple processes, physical processes, that have efficiencies associated with them. First one is regarding some mechanical gears. So what a gear does is you have to put a torque in, or a certain amount of work into this gear, causing the second gear to turn. Now, due to friction, all the energy that I put into the first one may not come out of the second one. So, for example, if I put 5 units of energy into that, this gear may only go ahead and give me 4 units of energy out. So my efficiency there is 4/5, or 80%. And that last unit of energy that I lost is usually lost as, in this example, would be lost to friction. The bottom I show another example where we have a water pump. And so we're putting energy into the water pump in order to increase the potential energy of this water. So what we're desiring is a change in potential energy. And we're having to put energy into the pump. So this pump would have an efficiency there. So the change of potential energy would be equal to the efficiency of my pump times any electric work that I put into that. Okay, let's go ahead and do a numeric example here, where what I have is a turbine. This is a kinetic energy turbine. It's 50% efficient. It's connected to a generator that is 90% efficient. I want to find out how much electric work I get out given these inlet conditions of 2 kilograms per second at a velocity of 5 meters per second. So what I've got going in here is some kinetic energy, a rate of kinetic energy, which is 1/2 the mass times the velocity squared. We can go ahead and figure out what that number is. 1/2 the mass flow rate of 2, and the velocity of 5 squared. We've got those cancel, 5 squared, or 25, and the units on this would be watts. And now to get the electric work, I'm going to go ahead and just multiply efficiency 1 by efficiency 2 by my 25 watts. So I have 0.5 and 0.9 and 25. So if I go ahead and multiply that, I realize that's 11.25 watts. So of the 25 watts of kinetic energy that goes in, 11.25 is coming out in the electric generator, and the rest are lost.